Here, we will learn how to define the polarization state of an EM wave. As we know, the direction of E field of an EM wave will change with time as it propagates. To define the polarization of an EM wave, we consider the direction of the electric field. You may wonder why we choose the direction of the E field to define the polarization state. This is because the H field and the E field, both these fields are perpendicular to the propagation direction. As a result, the direction of the H field is related to the direction of E field. So we don't have to consider the direction of these two fields together. We can just consider one direction. So we choose the direction of the E field to define the polarization state. And then we consider the E field of an EM wave in a simple medium. The E field can be written in the following equation. E of RT is equal to A vector, here is the amplitude of the E field, times cosine omega t minus K dot R. And we all know that K vector here represents the wave number vector, which is the direction of the wave propagation. And as a result, we know that in the space, the direction of K should be perpendicular to the direction of E. So K vector dot E will be 0. And to simplify our discussion, we suppose that this wave is propagating along the Z direction. Due to the E field and the H field, these fields are perpendicular to the direction of propagation. As a result, we know that both E field and the H field, they are lying in the transverse plane. You see, the direction of the wave is Z, so the transplane of the transplane to the Z should be the XY plane. So this means that the E field and the H field, both these fields are lying in the XY plane. So we can write the E field in the following form. Since the E field is in the XY plane, it may have two components, that is X component and Y component. So we express the x component in this way. E sub s equals to ax times cosine omega t minus kz. The duration, this is the duration of the wave, plus the constant phase delta x. And the y component of E can be written as a sub y times cosine omega t minus kz plus the corresponding phase delta y. And here, the delta x and the delta y, they should be in the range. They should be larger than minus pi, larger or equal to minus pi, and smaller or equals to plus pi. This is the general expression for the E component, as we suppose that the wave is propagating along the z direction. To find out the polarization of this EM wave, and we can choose the simple point to define the polarization. That is, we can choose the position at z equals 0 to define the polarization. Because as we choose the point z equals to 0, we can have simpler form of the EX and the EY. That is, we will then have E sub s is ax cosine omega t plus delta sub s, and E sub y can be expressed as a sub y times cosine omega t plus delta y. This means that no matter what's the value of z, they should have the EM wave should have the same polarization state. As a result, we can choose the easier point for us to define the polarization state. Besides, we define the relative phase difference here. We define a parameter called relative phase delta, and delta is defined as delta y minus delta x. According to the value of delta sub y and the delta sub s, we can know that delta should be in the range of between pi and minus pi. Using the parameter defined here, we will try to discuss all kinds of polarization states in the following slides. The first polarization we consider is the linear polarization states. For linear polarization, the E field always points to the same direction. If the E field of an EM wave always points to the same direction, we call it the linear polarization state. For such kind of polarization, we can have the condition that the relative phase delta, which is defined as delta sub y minus delta sub s, should be 0 or pi. Then it can be the linear polarization. For such kind of condition, we can find out the ratio of EY over EX equals to AY over AX. This means that the phase of these two components are the same, so the ratio of these two components is equal to the amplitude of these two components. Or the ratio will be minus AY over AX, which corresponding to the condition of the phase difference is pi. The figure in the right-hand side shows an example of the linear polarization. As the if component EX and EY, they have a fixed ratio, so the total E field will have the fixed angle to the x-axis and to the y-axis. As a result, you can see that the direction of the E field, it points to the same direction with time, like this. So we call it linear polarization. And in the space, you can see that the direction of the E field points to the positive direction, point to the negative direction, and point to the positive direction again. And if you see all these directions in a space, it will form a plane in this space, like this, a plane in this space. So linear polarization state is also called plane polarized. Wave. Okay? Due to this direction will form a plane, always in the same plane of the space. The next example is circular polarization state. The circular polarization state is defined as the trace of the E field in the xy plane is a circle. To have such kind of polarization, we have to satisfy two conditions. The first condition is that the amplitude of EX and the amplitude of EY should be equal to each other. That is, the AX should be equal to AY, and we can define these two as A. And the second condition is that the phase difference delta, which is defined as delta sub y minus delta sub s, should be the value of half pi or minus half pi. For EM wave satisfy these two conditions, it will form the circular polarization state. So let's see the two conditions here. First, we consider that if the phase difference delta here is minus half pi. By the definition of the delta here, we can know that under this condition, the delta sub y can be expressed as minus half pi plus delta sub s. As a result, we can rewrite the xy component of the E field in the following way. The E sub s can be expressed as A, amplitude A sub s become A here, times cosine omega t plus delta sub s. And the y component of the E field E sub y is A times cosine omega t plus delta sub y. And we can replace the delta sub y in this form and we can rewrite it as a times cosine omega t plus delta sub s minus half pi. And from the sinusoidal function, we know that for cosine function in this form, it will be equal to a times sine omega t plus delta sub x. And now we try to use these two results to see what's the properties of this circular polarization state. Okay, we start with omega t plus delta sub s is 0. As this phase is 0, we know that the Ex will be 1 and the Ey will be 0. So we start from this point. And as we know, as time is increased, this term will be increased positively. So the Ex component will be reduced and the Ey component will be increased positively. So as time increased, the trace of the E direction will in as the green dots here. So you can see that as time increased, the trace of the E field will form a circle in the counterclockwise direction. If you use the thumb of your right hand as the duration of the wave, then you will find out that your fingers just match the direction of the trace of the E field. As a result, we call such kind of polarization as right hand circularly polarized. Okay, so use your thumb as the direction of the wave. I shall plug K, and you will find out that your fingers is in the counterclockwise direction. As a result, we call such kind of wave as right hand circularly polarized wave. For the other condition, as if the relative phase delta is positive half pi, then the S component of the E field is A times cosine omega t plus delta sub s, and the Y component of the E field is A times cosine omega t plus delta sub s plus half pi. And we can re-express the cosine function in the sine function. They will be minus a sine omega t plus delta sub s. And we also start with omega t plus delta sub s is 0. And the trace of the iteration will also start from this point. However, as time increased, the component of E sub s will be reduced to 0, but the component of the Ey will increase to negative value. So the trace of the E field will look like these red dots here as time increased. Again, use the thumb of your left hand as the duration of the wave. Then you will find out that the fingers of your right hand will just match the direction of the trace of the E field in the clockwise direction. So we call such kind of polarization as left hand circularly polarized. The final polarization state is the elliptic polarization state. For such kind of polarization state, the curve For such kind of polarization, the curved trace formed by the endpoint of the E field will be an ellipse in the xy plane. And we can write down the general form of the EX component and the EY component like this. For EX component, it can be written as A sub s cosine omega t plus delta sub x. Sorry, I should write down the plus kz plus delta sub s. And for the y component, it will be A sub y cosine times cosine omega t plus kz plus delta sub y. And after some mathematical arrangement, you can derive the following equation like this. And this one will be your homework, and try to derive this equation for the elliptic polarization state. Okay, and you will form for such kind of equation is describe the trace like the blue ellipse here. But it's very we don't like look it in this way, so we try to use coordinate transformation to form a normal elliptic equation for us. So by using coordinate transformation, we can rotate the xy coordinate to the x prime and the y prime coordinate. That is, rotate the original axis with a phi angle shown here. And the above equation will become ex prime over ax and the square plus the square of ey prime over a sub y. The summation of these two will be equal to 1. And this is the equation we familiar with. So I shall say that this is the equation of elliptics, which we are very familiar with. And to form such kind of equation here, the phi should be satisfy the condition. Tangent to phi is as this way. Okay, so by using the coordinate transformation, you can easily to transform such complicated expression into the simpler equation, which we are very familiar for an ellipse. That is the this definition of the elliptic polarization state. In the following slide, we will show you all kinds of polarization. For the above here, this means that the amplitude of x component is equal to the amplitude of y component. And under this condition, as delta is 0 or delta is pi, you will have the linear polarization. And as delta is minus half pi or delta is half pi, you will obtain the right-hand circularly polarized wave or the left-hand circularly polarized wave. For the other delta value, you will have elliptic polarization. And for polarization below here, this is an example for a sub x equals to half a sub y. And again, for such kind of phase difference, you will still have linear polarization. But for these two conditions for delta value, now you will have elliptic polarization due to the amplitude of these two components are not equal to each other. Okay, and again, for the other value of delta, you will obtain elliptic polarization for right hand and left hand. This is all kinds of polarization we consider here.